Ptolemy himself proved the addition formula in another way, using a remarkable property of quadrilaterals that can be inscribed in a circle. A quadrilateral is a polygon with 4 sides. Not every quadrilateral can be inscribed in a circle, but for those that can, the product of the lengths of these two opposite sides plus the product of the lengths of these two opposite sides is equal to the product of the lengths of the two diagonals. This equation is called Ptolemy's theorem, and it can be interpreted geometrically in terms of areas of rectangles. The equation is true no matter where the vertices lie on the circle. Now let's see why Ptolemy's theorem is true. These two angles are equal because they cut off the same chord. Rotate this triangle until this diagonal of length E lies along this edge of length B. The two shaded triangles are similar. Likewise, these two angles are equal because they cut off the same chord. So rotating this triangle reveals another pair of similar triangles. If we rotate both triangles, we see that they join along a common side that divides this diagonal of length F into two pieces of length X and Y. Now we have two pairs of similar triangles, so ratios of these corresponding sides are equal. And ratios of these corresponding sides are equal. And the rest is just a little algebra. The final result is Ptolemy's theorem on quadrilaterals inscribed in a circle. Let's see what happens when the quadrilateral is a rectangle. These two opposite sides have equal length. These two opposite sides have equal length. And the two diagonals have equal length. Surprise! Ptolemy's theorem becomes the Pythagorean theorem for right triangles. The sum of the squares of the legs is equal to the square of the hypotenuse. Now we'll use Ptolemy's theorem to derive addition formulas for both the sine and cosine. Start with the circle of diameter 1, take angle A, and form a right triangle. The lengths of its legs are sine A and cosine A. Use angle B to form another right triangle. The lengths of its legs are sine B and cosine B. The two triangles together form a quadrilateral inscribed in a circle, with one diagonal being a diameter of length 1. The length of the other diagonal is the sine of A plus B. Now apply Ptolemy's theorem. The product of the lengths of these two opposite sides plus the product of the lengths of these two opposite sides is equal to the product of the lengths of the diagonals. Presto, the addition formula for sines. To get an addition formula for cosines, first rotate this right triangle 180 degrees, so this diagonal is a diameter, and this triangle is a right triangle. The length of this leg is the sine of A plus B, so the lengths of this one must be the cosine of A plus B. Again, we have a quadrilateral inscribed in a circle, so we can apply Ptolemy's theorem. The product of the length of these two opposite sides plus the product of the lengths of these two opposite sides equals the product of the lengths of the two diagonals. When it's written this way, the result is the addition formula for cosines. It says the cosine of A plus B equals cosine A times cosine B minus sine A